morning, dear friends. Let us have the next lecture in the same unit. That is the theory of relativity. Today we will discuss the effect of velocity in the relativistic mechanics for the mass as well as for the velocity component. Here we will see that what will happen if we will consider the velocity component by being in the moving frame of reference or by being in the static frame of reference. So that is known as transformation of velocity component. Velocity components. Sometimes this topic is also termed as the theorem of addition of velocities. Addition of velocity. We will also justify how the speed of light is constant, and that we will see on the basis of these transformation equation related to the velocity component. And later on we will also see in the same lecture that if velocity remains no longer constant, then what will happen about the momentum of a particular particle, because we know that P is equal to mv. For example, this expression is here. Anyhow, if this v is not constant and this is changing with the change of frame of reference, then this law of conservation of momentum will be in trouble. And if anybody adamant to preserve the law of conservation of momentum, then he or she has to work out something for this m. Means m has to be changed or it has to be commensurated with the change in the velocity component. That also we will discuss in this lecture. And as a consequence, you will see here the velocity, the mass of body remains no longer constant, and hence we will be able to find the expression for the variation of mass, how the mass will vary with the velocity if it will be examined by being in the different frame of reference. The most important thing for these topics, what we have planned to discuss in this lecture, you will see that velocity is responsible much for all the things, and that is too comparable to the velocity of light, because all the discussion whatever we are making here, that is in the relativistic frame of reference or in the relativistic domain under the umbrella of theory of relativity or in the relativistic mechanics. So you will see if velocity will be very high, then the mass will vary. If velocity will be very high, then even the velocity component observed from the different frame of reference will be same, will be different. So here one slogan is in Hindi is here that if we will move with the higher velocity, then how the situation will change. Here let us see that one. आंधियों की जद में रहकर तो देखो, फनूस भी तीर नजर आएंगे, रोशनी की तर्ज पर चलकर तो देखो, खाक के जरे कहकसा कहलाएंगे. You will see from this statement or from these lines that if a particle of a bead will move with the tremendous velocity, that will behave just as an arrow, and if even at the dust particle starts to move with the velocity of light, then they will be the pathway for the stars. So that idea we will use here, how with the change in velocity mass of a body will vary. So for that, we will take first part of that, the transformation of velocity components. There is the velocity addition theorem. For that, as usual, what we used to do to discuss the topics related to the theory of relativity, especially in the relativistic mechanics, we consider two frame of references. As usual, what we did in almost all the lectures, and these two frame of references must be inertial in nature. It means that second frame of reference is moving with a constant velocity with respect to first one. Moving frame of reference is termed as the S dash frame of reference, and while the static one is as S frame of reference. Here O is the position of observer, here O dash is the position of observer, and all the axes will be termed in according to the selection of the frame of references. As S dash is here, then obviously X dash, Y dash, Z dash will be, as well as the T dash will be here, and the measurement from this frame of reference will be for the location and position of a particular particle, that X, Y, Z and T. Similarly, we will talk about the component of the velocity. Component of a velocity. For example, this particle is here and this particle have a particular velocity, that is V, having its component Vx, Vy and Vz in X, Y, Z direction. If that has been examined by the observer O here, then it will be termed as Ux, Uy and Uz. Means that these are the three components of velocity of this particle P observed by the observer by being in the static frame of reference. Now if the same thing has been observed by the observer O dash, then this will be equal to Ux dash and Uy dash and Uz dash. In this particular topic or in this theorem, we have to discuss that what will be the relation between these two components. You might remember one relation has been suggested by the Galileo himself. If you remember, then you will see that there was Ux dash, this will be equal to Ux minus V, and that depends that what value of the velocity we have taken by being in the different frame of reference. So this was suggested by the Galileo, but we have to see that the same type of relation will be here or something else is there. So in order to examine that, we will use the basic equation or the basic representation for the velocity component, that is Ux, Uy, Uz, as well as Ux dash, Uy dash and Uz dash. So as usual, we have read that Ux, that is the x component of the velocity, that's why we will write it as dx upon dt. Very simple. Similarly, Uy will be equal to Uy upon dt and Uz is equal to dz upon dt. Similarly, we will talk about the components of the velocity of a same particle observed by the observer by being in the moving frame of reference. Then it will be equal to Ux dash and this will be equal to dx dash upon dt dash. Uy dash is equal to dy dash upon dt dash and Uz is equal to dz dash upon dt dash. This should be the relation. Now we have to examine that what relation will be here between x component of the velocity to the x dash component of the velocity, y component of the velocity, y dash component of the velocity, z component of the velocity, and z dash component of the velocity. So for that we will start from the basic transformation equation, which has been suggested by the Lorentz, that is known as the real relativistic transformation equation, that has been derived on the basis of the postulates of special theory of relativity. Means that the concept of the special theory of relativity has been included to derive the Lorentz transformation equation, which are known as the real relativistic transformation equation. So in order to have this one, obviously here x is there, here t is here, y is here, x dash is here, y dash is here, z is here, z dash is here. And we must remember that what are the relation between x and x dash, y and y dash, z and z dash, t and t dash. So in order to use that, we will start from those relations, and let us write the inverse Lorentz transformation equation for the x component. Then it will be equal to x dash plus v time vt upon, here we will have under root vt dash upon 1 minus v square upon c square. Here we have this one. We have started from the component. This is the x component, y component, z component, x dash component, y dash component, and z dash component. And x dash we are writing here. X is equal to x dash plus vt dash upon under root 1 minus v square upon c square. There is no change in y component. Why? Because there is no motion along y and z direction. X dash is moving only along x axis. That's why the change will be only in x component. Only in x component. Since x component remains no longer constant as this component, that's why t will also be changed, because t depends on the x component here, That's why we will write here z is equal to z dash, and t will be equal to t dash plus here v and x dash upon c square upon under root 1 minus v square upon c square. These are the. Now we will take the differential change in this one, differential change in this one, differential change in this one, differential change in this one. Then according to that we will have the different value, and we will write here dx is equal to dx dash plus vt dash divided by under root 1 minus v square upon c square, or simply we will write it as dx is equal to gamma times, gamma means that is 1 upon under root 1 minus v square upon c square. Sometimes this factor we will use as a k also. So either you are writing k or you are writing gamma. In some books it has been mentioned as a gamma, in some books it has been mentioned as a k, but it hardly matters. K and gamma are the same thing, having its value 1 upon under root 1 minus v square upon c square. So we have this particular value. So here we will write that dx is equal to dx dash plus v times dt dash, and this will be multiplied by gamma k. It will be better k because we are writing k here. Here we are writing k. K is equal to 1 upon under root 1 minus v square upon c square. Similarly, we will write the differential form of the other component. Dy will be equal to dy dash. There is no change at all, and dz will be equal to dz dash And when we will write the differential form of this one, then differential change in t dt will be given as dt dash plus v dx dash upon c square, and this whole will be divided by under root 1 minus v square upon c square. This term may be treated as a k because 1 upon under root 1 minus v square upon c square is treated as a k. So here we may write it here, dt is equal to k times dt dash plus v upon c square dx dash. This will be the value. Now in order to find the value of x component of velocity, x component of velocity means change in the direction of x in a particular time, let that time is dt. So this ux will be equal to dx upon dt, and we know that what is the value of dx here, that is k times dx dash plus vt dash, and this will be divided by k times dt dash plus v upon c square into dx dash. This will be the obviously k and k will be cancelled out, and ux will be given as dx dash plus vt dash v dt dash upon dt dash plus v upon c square dx dash. Better to take dt dash as a common in the numerator and denominator both. We will see, or we will do it. Then dt dash as a common, then it will be dx dash upon dt dash, and it will be plus v only, divided by dt dash we have taken as a common 1 plus v upon c square, and dx dash upon dt dash. This will be here, dt dash and dt dash will cancel to each other, and final expression for ux we can write here in this way. ux is equal to dx dash upon dt. What is this one? You will see here. ux dash is equal to dx dash upon dt. In place of this we can write, and it will be ux dash plus v is here, and divided by the quantity 1 plus v upon c square, and it is equal to ux dash again because dx dash upon dt dash. So this will be the transformation of the velocity component in x direction, and we will talk about the transformation of other component, that is y and z component. Let us see that what we will have. Obviously this uy is equal to dy upon dy dash, because here y is equal to y dash, and this d uy component is dy upon dt. In this we know that this dy will be equal to dy dash because y is equal to y dash. That's why dy is equal to dy dash. And in place of dt, what we will use, which earlier we have the expression of t. That's why here dt dash plus v upon c square dx dash upon under root 1 minus v square upon c square. Let us use this value and let's see that what expression we will have. So it will be equal to dy dash upon dt dash plus v upon c square multiplied by dx dash, and this entire will be divided by under root 1 minus v square upon c square. This will be the expression in the denominator. this is corresponding to the value of dt, because here dt is equal to dt dash plus v dx dash upon c square upon under root 1 minus v square upon c square. So for our sake of convenience, we may write it as this factor, we may write as a k, then we may write it as uy will be equal to this dy dash divided by dt dash as a common, then we'll have 1 plus v upon c square, and here dx dash upon dt dash, and here is the denominator under root 1 minus v square upon c square. So for our convenience, we may write it as a k, and this k will be here because this k is equal to 1 upon under root 1 minus v square upon c square. And by doing this one, you may transfer this dt dash with this dy dash. Simply you may write it as dt dash upon dy dash upon dt dash. That will corresponding to what value? This is corresponding to y component in s dash coordinate. That's why we will write it as uy dash. This we will write uy dash, and in the denominator we will have k times 1 plus v upon c square, and here we will have ux dash because dx dash upon dt dash. This is corresponding to this. So uy will be equal to this uy dash divided by k times 1 plus v upon c square into ux dash. Very important observation you may have here. The component of velocity in x direction have something else relation between dash and non-dash coordinates, while this component, y component, have the different observation. Different observation means this uy will be equal to uy dash upon something else which is different from the x component of the velocity. So similarly, let us test that what will happen for the z component, and for the z component we will write the expression in the similar way, but better to realize it. Maybe that would be different from the earlier case, but if it will be same, then it we will write as such as we did in the case of y component. For the z component, we will write uz, and this uz is equal to dz upon dt. So again we have to write the value of dz. Dz means z component, and for z component we will write its transformation equation. Why? Because we wish to transform the z component, which is the non-dash in the non-dash coordinate system, to the dash coordinate system. So we will write here that dz dash. Dz dash means that dz dash means dz dash, because here z is equal to z dash in the according to the Lorentz transformation. Why? Because along z axis there is no change in the velocity. The velocity is changing only along x axis, because s dash frame of reference is moving along x axis. So we will write here dz and for dz dash, and for this t component, we will use the expression what already I have discussed for the t, and it will be equal to dt dash plus v upon c square into dx dash divided by under root 1 minus v square upon c square. And if we will do it, then you will see here that again t dash will be taken as a common in the denominator. Then finally we will write here dz dash divided by dt dash, and here in the denominator we'll have 1 plus v upon c square, and since we have taken dt dash as a common, then it will be dx dash upon dt dash, that will be corresponding to ux dash, and there is a quantity here in the denominator, that's why we will write it as a k here as a multiplier. And the final relation between z component of velocity as well as z dash component of the velocity will have uz is equal to uz dash divided by k times k times within bracket, here what we are taking 1 plus v upon c square into ux dash. This will be the value. And similarly, already in the just a moment before we have derived that what will be the expression corresponding to the z component. Corresponding to the z component, you will see y component. So you will see that the y along y component will have uy is equal to uy dash divided by k times 1 plus v upon c square into ux dash. So these are the relation between the components of velocity which has been observed in the limelight of the Lorentz transformation equations. Here what has been observed in the continuous evaluation of our student, many times we have observed in their answer sheets what they used to do actually. They used to derive this expression first, that ux is equal to ux dash plus v upon 1 plus v upon c square into ux dash, and then after they don't take care of other transformation equation, but they write here directly. Similarly, ui is equal to ui dash plus v upon 1 plus v upon c square into ui dash, and their answer become wrong because this x direction is entirely different from y as well as of z. You may write it as you may write that after deriving the expression or the relation between the y component of the velocity extended for the z component exactly same, because the situation along y axis as well as along z axis is same, but it is different for the x component. That's why whenever you are deriving this relation, you should take care of this one. There is another alternative method what I have suggested in the text also. If you will see here, it is very interesting also, but I feel that a student has given the feedback that the first part what I already have discussed with you people, that will be more easy for them rather this one. But if anybody is interested, then they may have this alternative method for the derivation of the relation between the x and x dash component, y and y dash component, z and z dash component of the velocity. Here we have taken first what we have taken here. First we wrote the expression for t, that is t is equal to what, t is equal to t dash plus v upon c square dt dx dash upon dt dash. In this way, similarly you may see it because one step, first step is missing here. If we are writing that what is the relation between t and t dash, then obviously we will write from the inverse Lorentz transformation t dash plus v upon c square into x dash divided by under root 1 minus v square upon c square. If we will write it, if we will differentiate the entire expression with respect to t, then dt upon dt dash, and this will be equal to here with respect to t dash we are differentiating, that's why 1 will be here, and 1 plus v upon c square dx dash upon dt dash, and here in the denominator we will have 1 minus v square upon c square, and what has been written here in this expression. Now we have taken dt upon dt dash, and here we may have gamma or k, whatever the constant you are taking. If gamma we will take, this gamma will have the same value, that is 1 upon under root 1 minus v square upon c square. This way is gamma 1 plus v upon c square, and here we will have ux dash, this will be the value. And gamma has been defined also here. What is the gamma value? Ux is equal to what? Ux is equal to dx upon dt. Ux is equal to what? Dx upon dt. Means that we will write this value and we will write it as such, because later on we will have the use of this expression. What is the value of dt upon dt dash? It will be required in the intermediate stage of our derivation for x, y and z component. So if you are writing ux, then it is equal to dx dash upon dt dash. Kyun? Because this is equal to dx upon dt, and corresponding to the x we have x dash, corresponding to t we have t dash, when we are using the transformation concept for the velocity from one reference to the other reference. So we will have here dx dash are similarly here one more thing has been taken into the consideration that will be better to understand here. The entire expression has been taken in this way, d by dt of x, for example. So d by dt, here we have written the transformation of x component. Then first we will write gamma is outside because it is a constant, and here we will have x dash plus vt dash, here x dash plus vt dash. If we will differentiate it, then what we will get, that is important here. Gamma times, let us differentiate it with respect to t, but it is in dash coordinate system and it is in non-dash coordinate system. That's why we cannot differentiate dx dash with the dt. If we are doing the same, then that will be meaningless, because one quantity we are taking in the dash coordinate and other we are taking in the non-dash coordinate. That's why it will have no meaning at all. Similar question you may ask, that why you are writing this one, why you are writing this one, dt upon dt dash, it will also have no meaning. So for a kind information, we are writing this expression for not any particular meaning, since this quantity just as a ratio will be required in the intermediate stage of our derivation. That's why we have computed just the value of this one. So here we will differentiate it with respect to the same coordinate system. Same coordinate system is, if we wish to differentiate it, then we will differentiate it dx dash upon dt dash, and now we will differentiate this t dash with respect to t, and plus v dt dash upon dt. Now you might remember this thing, why I have computed the value of dt upon dt dash, because it will be required here, and we have this quantity as a common in this expression, because it will be required. That's why I am not writing it dt dash. Here let us take dt dash upon dt as a common, then gamma times dt dash upon dt, and within bracket we'll have ux dash plus v, and if we will put this value, is that the reciprocal of this is lying here as a gamma times 1 plus v upon c square into ux dash. So that's why we write here, and using this we may write it as d upon dt dx upon dt. This is equal to here ux dash here what we have taken in this expression, ux dash gamma times ux dash plus v, what we have taken here, and here we'll have the reciprocal of this one, 1 upon this one. 1 upon this one is gamma here, and 1 plus v upon c square into ux dash, gamma will cancel out. We will have x component of velocity, that is ux, it will be equal to ux dash plus v upon 1 plus v upon c square ux dash. This will be the x component of the velocity and their relation when we are observing it by being in the different frame of reference. Similarly, we can find that what will be the relation between the y component of velocity when it is observed by being in the moving frame of reference and static frame of reference. Then you write uy, this is equal to d by dt of y, and by putting the value of this y, we will write dy dash upon dt, and since again it have no meaning because one is in the dash coordinate system, another is a non-dash coordinate system. That's why we have to write it just as a meaningful entity. That's why we will write it as d by dt dash of y dash multiplied by dt dash upon dt. By putting the value of this one again, you will have uy dash upon gamma times the quantity already we have computed, and that have 1 plus v ux dash upon c square. This is the transformation of y component. Similarly, we can write the z component, what has been shown here in this expression. This is corresponding to the y component, and this is corresponding to the z component. So this is an alternative method for that. Here one most important point what already I have discussed during the discussion of the postulates of special theory of relativity, in which the Einstein was suggested that the speed of light remains constant. It has nothing to do with the position of source and observer. Whatever the position of source, whatever the position of observer, c will be always c. It will never be c plus b or c minus b. That can be verified from this expression what we have derived for the x component. Ux is equal to ux dash plus v divided by 1 plus v upon c square ux dash. Here we have taken that the component of velocity in moving frame of reference is equal to c. Then let us see that what will be the value of ux. For that, let us put in place of ux dash as a c. In place of ux dash, we are putting here c, because here we are considering that if ux dash is equal to c, then observe that what will be the value of ux. So in order to examine this one, let us put the value of ux dash here. Ux is equal to c plus v divided by 1 plus v upon c square into c, and 1 power of z will cancel out, and here we will have c plus v divided by c plus v divided by c, and finally it is equal to c. What has been observed? That is very much clear from this expression also. Okay, if we are taking the velocity of particle in moving frame of reference as a c, then it will be c in the other frame of reference also. There will be no effect of transformation of the velocity component what has been taken into the consideration as we have discussed in the velocity addition theorem. There is the expression which reveals this fact that definitely the constancy of speed of light, that is the second postulate of special theory of relativity, has been verified here in this expression. Now the most important fact and point what we are going to discuss here, if we are considering that the velocity remains no longer constant, then how we can preserve the law of conservation of momentum? Usually there is no violation of the law of conservation of momentum and the law of conservation of energy. That's why it must be preserved under the postulates of special theory of relativity or under the relativistic transformation equations also. That's why if anyhow we are writing that m1v1 is equal to m2v2. For example, we have taken this simple expression of the law of conservation of momentum, what we might have read in our lower classes, कि momentum before any particular event and momentum after that event, that will be same, there will be no change. So if we will observe this law of conservation of momentum, then since this v1 and v2, if these two velocities are observed by the observer by being in the different frame of reference, then v1 and v2 will not be same and they will change according to the velocity addition theorem or the transformation of the velocity equation. So this law of conservation of momentum will be in trouble. If anybody wishes to preserve this law of conservation of momentum, then definitely he or she has to take care of that, what will happen with the mass of that particular body, and the mass has to be changed according to change in velocity in order to preserve the law of conservation of momentum. And as a simple case we can consider, the law of conservation of momentum can be preserved on the cost of the variation of the mass of a body, and the basic concept for the variation of mass begin from this particular point. And you can see or you can consider that this is the origin of the thinking for the variation of a mass of a body with the velocity. Here, in order to derive that, let us recall our memory what we have read in our lower classes, that the variation in the mass of a body will be as m is equal to m0 upon under root 1 minus v square upon c square. We have solved so many equations, so many problems related to this one, but up to this level we not have realized that how we came at this particular relation, how we have realized this particular relation. That can be realized only using the postulates of special theory of relativity or using the relativistic Lorentz transformation equation and transformation of the velocity component. Here, in order to discuss this change in mass of a body, let us observe this particular figure what we have sketched, and just in a simple way. Here we have ball A, here we have ball B. These two balls are in the moving frame of reference, that is in S dash frame of reference. And these two balls A and B have the same mass, like it is mass M, it is also the mass M, and both have the same speed but they are in opposite direction. So this ball A is moving in this direction having the speed u, and this ball B is moving in this direction having the speed u, but the velocity will be minus v because the direction has been changed. Now what will happen when these two masses will come together? Just these two balls are coming together, and since they are moving with the same velocity, when they come to each other, then they will stuck and they will form the coalesced mass of ball A as well as of ball B. What has been taken here? M plus M. So this is the observation taken by the observer who is in this moving frame of reference. Moving frame of reference observer says that this ball is moving in this direction by u velocity. This ball B is moving in this direction by the minus v velocity, having the same mass, and after the collision they will have the mass m plus m. Now what will happen to the observation taken by the observer by being in the static frame of reference? The observer will say that I am seeing the different thing. What has been revealed by the observer in the moving frame of reference. He or she will say, no, its velocity is not u, that is u1, and the velocity of this b is not minus u, this is u2, and corresponding to that maybe that the mass of ball A is equal to m1 and mass of ball B is equal to m2. Now in the limelight of the observation taken by the observer O as well as of O dash, try to preserve the law of conservation of momentum. First we will write the law of conservation of momentum for this frame of reference, and for this frame of reference if you write, then we will see that mass of ball A multiplied by its speed plus mass of ball B multiplied by its velocity, and this will be equal to after the collision. After the collision, what is? Both has been joined and stuck to each other to have a coalesced mass, and if they will have the coalesced mass, then they will stop their motion. Neither ball A will go in this direction nor ball B will go in this direction, rather they are forming a coalesced mass, and that will be static. That coalesced mass is not moving either in this direction or in that direction. That's why here we will have zero velocity. If we write here, then mu minus mu, this will be equal to m plus m multiplied by 0, and here you will see 0 is equal to 0. Hence the law of conservation of momentum will be valid if the observation has been taken by being in the moving frame of reference or by being in the same frame of reference in which really the balls has been placed, and they are supposed to move in the opposite direction and they are forming the coalesced mass after the collision. Now if the same thing has been observed by being in the moving frame of reference, then the observer will say that let us try to have the law of conservation of momentum, and in that we will write m1 u1 plus m2 u2, this will be equal to after the collision here, collision is taking place here, observation has been taken from this frame of reference, then before the collision this situation will prevail. It appears that it is moving with the velocity u1, this is moving with the velocity u2, corresponding to the masses has been considered m1 and m2 respectively. Here when they will stick to form a coalesced mass, then really they will be static in this frame of reference. But what will be observed by the observer in the static frame of reference? He or she will say that the coalesced mass appears to move with the velocity by which the second frame of reference is moving. This frame of reference, because this is moving with a particular velocity, and the things has been placed here, although here it is static, but since it is moving with the velocity v, that's why this observer will say that the coalesced mass is moving with the same velocity with which the second frame of reference is moving. That's why we will write here m1 plus m2 multiplied by v velocity by which the second frame of reference is moving. Now let us write the value of u1, write the value of u2 according to the velocity transformation equation, because if we will write here u1, then u1 will be with a particular expression what I have written here, that u1 is equal to u plus v upon 1 plus uv upon c square, u2 is equal to minus u plus v upon 1 minus uv upon c square. By putting these values here we are putting the value of u1, here we are putting the value of u2, and here m1 plus m2 into v. I have already explained that why we are writing u here and v here, because this v velocity second frame of reference is moving. By calculating these, we will have the m1 multiplied by m2 multiplied by this much. Just we have transferred that m1 has been transferred here, m2 has been transferred there, and just using the simple mathematical operation, we will have m1 upon m2. This will be equal to 1 plus uv upon c square, and this will be divided by 1 minus uv upon c square. Let this equation is 1, and again we will start from a particular expression, that what will be the value of 1 minus u1 square upon c square. If we have to do this one, then we have to write the value of this u1. For that we will write 1 minus u1 means u plus v upon 1 plus uv upon c square, and whole will be divided by c square. And since this is square, that's why this will be also square. For our sake of convenience, what we will do here, that the c square we will take here, and this expression will be 1 minus u plus v upon c whole square, and this entire will be divided by 1 plus uv upon c square whole square. Now you may see that it was the c square. This c square has been absorbed here. That's why u plus v upon c whole square we have taken here. And if we will realize it, then 1 minus here we will write u square plus v square, here c square, here c square, here we will write here 2uv upon c square, because the c square will be in all the terms, and this is a plus b, that's why a square plus b square plus 2ab. So, and it will be constantly will be divided in all the terms of there, and this will be with a negative sign. You may put here it in place of 1, because by taking the LCM you may write it as 1 plus u square v square upon c to the power 4 plus 2 times u v upon c square, and here will be the negative sign, and this will be divided by 1 plus uv upon c square whole square. And when you will open the bracket, and you will see here 2uv square upon c square, they will cancel out, and by taking the suitable terms common, you will see that this value will have this value here this form is here 1 minus u square u1 square upon c square, 1 minus u1 square upon c square. This will be equal to 1 minus u square upon c square, and here 1 minus v square upon c square. The whole is divided by 1 plus uv upon c square whole square. This will be the expression. Similarly, if we will do the same task for 1 minus u2 square upon c square, but the same type of expression we will get. The difference will be what? That here 1 minus uv upon c square whole square will be here. What has been written here. And if we will compare the right hand side to the equation number 1, what already I have written there, then finally we will write this expression m1 upon m2. m1 upon m2, this m1 upon m2, this will be equal to under root 1 minus u2 square upon c square and this will be divided by under root 1 minus u1 square upon c square, and we will have to take the cross multiplication of this. Then we might have m2 root 1 minus u2 square upon c square. This is equal to m1 under root 1 minus u1 square upon the square, and similarly we will have the more component, that is u3 square upon c square u4. Then that will be the constant. You may write this is equal to dot dot dot, and this will be a constant quantity. What you will observe here, that the variation in mass of a body will be compensated or will be commensurated with the velocity of that particular body, and that will be always equal to a constant quantity. Let this constant is m0, and finally we may write m1 is equal to m0 upon under root 1 minus u2 square u1 square upon c square, or m2 is equal to m0 upon under root 1 minus into u2 square upon c square, or in general expression we can write that m is equal to m0 upon under root 1 minus v square upon c square. This is the desired expression what we used to write for the variation of mass of a body, and we might have enjoyed this particular expression in so many earlier cases in our lower classes, but the derivation we have taken here, how we can derive the expression, and finally you may see here this is the expression for the variation of mass. Here this is very interesting event, that f is equal to m0a and m0 into change in velocity upon time, because this a is the acceleration, that acceleration is change in velocity upon time, and here time t0 in the moving frame of reference can be written as change in v is equal to ft0 upon m0 by using this expression, and this m0 will be equal to ft0 upon change in velocity v, and finally here we will write that m is equal to ft upon change in v, and t is equal to gamma times t0, because when the time will be observed by this person as the earth for the clock which is in the moving frame of reference, the time will be dilated, and that dilated time relation can be written as t is equal to gamma times t0, and by putting this value we will have gamma times ft0 upon change in velocity, and finally we will write it here that gamma times m0, gamma is equal to what? Gamma is equal to 1 upon under root 1 minus v square upon c square. That's why finally we will have the relation of mass in the moving frame of reference and in a static frame of reference, or simply the expression for the varied mass. And here rest mass will be m0, means mass of the object when it is at rest, and mass of a moving object when it is moving with the velocity v, and that will change obviously by a factor of v. And if we will plot the graph corresponding to that, then you will see that as the velocity is changing, the mass is changing. When v will be equal to c, then the mass of a body will be almost infinite, or it will tend to the infinite value of the same. Here this expression reveals that v is equal to c, then m is equal to m0, because in the denominator of the expression of the varied mass, that is m is equal to m0 upon 1 minus v under root 1 minus v square upon c square. If v is equal to c, then it will be 0 and it will tend to the infinite value. So as an object moves faster, it gets harder and harder to accelerate. This is the expression. Some conceptual question is here. You may have the practice for these questions. S dash frame of reference is here, in which the coordinates are written in this way, and we have to prove that the same types of equation will prevail if the situation will be observed by being in the static frame of reference. And finally, this ux has been written, uy has been written. By putting the value of ux and uy and solving this one, we have c square, and hence we will have the invariance of this expression, that is ux square plus uy square is equal to c square. Similarly, this is very easy and very interesting question. Okay, if a body has been driven with a particular velocity, with what velocity it should move so that it should attain its mass is equal to 1.5 times of its earlier value. Means that earlier value means its rest mass. So here this expression is m is equal to, m is the varied mass, and 3 by 2 into m0, that is the rest mass, m0 is the rest mass. And if we will compare here, m0 upon under root 1 minus v square upon c square, this is given that this is equal to 3 by 2 of m0. By putting the values of this one, we will have finally the value of v, that is c root 5 upon 3. One task has been given, if a stick is moving with such a velocity by which its mass changes by a factor 3 by 2, then how much the shrinking, how much contraction in the length of the rod will be there. So you will have the value of v with what velocity our stick is moving, and here we have the contraction relation, that Vl is equal to L0 under root 1 minus v square upon c square. By putting the value of v, finally you will have L is equal to 2 by 3 meter. It gives the fact that 66.7% contraction will be observed in the length of the rod. As far as assignment is concerned, you should make the practice for this. How the velocity components change with velocity, means that you have to derive the velocity action theory. Next point is what we have to do our practice. How these are different from the Galilean transformation of velocity component. Here in this expression, you have to compare the velocity addition equation which has been suggested by the Galileo and what has been observed under the consideration of the Lorentz transformation equation, and how these are varying by taking the concept of a special theory of relativity. Here, show the addition of velocity component and prove the constancy of speed of light. Already I have proved it, that if ux dash is equal to c, then what will be the value of ux, that already we have discussed there. How the relativistic velocity addition theorem suggests the variation of mass with velocity. Basic fundamental concept what already I have discussed, if the component of velocity remains no longer constant, then the law of conservation of momentum will be in trouble. And if anybody is adamant to preserve the law of conservation of momentum, then that can be done only on the cost of the variation of the mass of the body. That we have to do and we have to realize here. Using the concept of the theory of relativity, obtain the expression of the variation of mass with velocity. Explain the concept of infinite mass of a body moving with the velocity of light. It will be better when we will go to the next unit of engineering physics, when we will start the mass energy equivalence, or one step more than the mass energy equivalence. How if the particle is moving with the tremendous velocity, so no longer it remains as a particle, it will be converted into the wave. And in that situation, how the infinite mass of a body can be explained, we will deal there. Here only you have to explain this fact on the basis of the expression what I have written here, m is equal to m0 upon under root 1 minus v square upon c square. So this is all about of today. In the next lecture we will meet to have the more discussions.